Good morning. Okay, good morning, everybody. So we're going to proceed with lecture 12, the topics of applications of Fourier transform. Okay, so this is a continuation from what we have learned from previous lecture 10 and lecture 11. So just to recall the things that we have learned so far in chapter 3 on Fourier transform. So we have learned about the properties of Fourier transform, yeah, in two lectures 10 and 11. So a few properties have been visited so far. Okay. Right. So we're going to continue now with the applications of Fourier transform, in which we are going to utilize those properties that we have learned so far. Yeah. Right. So this is the excerpt from your course information. Right. So we have covered the two topics above here, Fourier integral and Fourier transform theorem properties. So we're going to proceed now with the applications of Fourier transform, which is covering the topics of modulation, yeah, modulation and also filtering, yeah, modulation and filtering. Okay, right. So two applications will be covered in this lecture 12. The first one will be on the filters, okay, on the filters, and followed by the AM or amplitude modulation. Okay, yeah. Okay, so this is a things about filters that I think most of you or all of you knows about filters, yeah. So basically filters is a component used in signal processing application in which we use for the voice, data and video. So normally we use it for frequency filtering, yeah. We will want to filter the frequencies, okay, in which basically the functions or the applications or the filters used to permit certain frequencies and also to block other frequencies. Yeah, so the permission to allow or allowing the frequencies or blocking the frequencies will be depending on the specification that have been set earlier. Yeah. Okay, so this is a graphical representation of the filters in which if we have 5 different frequencies value, let's say we have omega naught up to omega 4. So depending on the filter's design specification, we are getting or we are allowing only 2 frequencies, for instance, omega naught and omega 1. So the rest, omega 2, omega 3, and omega 4 are said to be blocked. Yeah. So this is the filters. Yeah, the application of filters, which is to block frequencies and to permit certain frequencies to pass through. Yeah. Okay. So filter basically is one of our main topic in this course. So we're going to learn this in detail in chapter 5 when we learn about the Bode diagram or Bode plot and also the filter design. Yeah. Okay. So this is and how we apply the Fourier transform. Yeah, in understanding what the filters application. Okay, so for instance, if we have in this diagram, we have 2 inputs to the system. We have AT, we have the BT, okay, and this multiplication of the signals will create the CT signals, okay. So the CT will pass through the filters, which is having a frequency response or a transfer function of H omega, and we are getting the output of DT, yeah. Okay, so for instance, let us consider two the AT and BT to be having these values or frequencies, in which we're assuming that the AT is a signal with a frequency of 100 pi, yeah, 100 pi, while the BT is a frequencies of 500 pi frequencies. So this is based on the cosine terms, yeah, AT is a cosine terms, and the same things for the BT is also a cosine terms, but with different frequencies, okay. So the AT is exponential j 100 pi t, plus exponential negative j 100 pi t divided by 2, while the bt is in these terms, 2 exponential j 500 pi t plus exponential negative j 500 pi t divided by 2. So based on these values of a, b, okay, we are supposed to get the ct, yeah, which is a result of multiplication of both signals, in which your ct should be written as this, okay, in which the ct should be in two different frequencies value, which are the 600 pi frequencies and also the 400 pi frequencies, yeah, because of these uh, operations, yeah, between two cosine function, so the output should be having two different frequencies here, yeah. So it can be said now, if we go back to the previous slide, okay. So it means that if we are referring to this filter, so two signals frequencies will pass through, which are the 400 pi and 600 pi frequencies value, yeah. So depending on the design spec of the filters, we will be having four different conditions, yeah, four different conditions for the DT output, yeah, depending on how we design the filter, okay. So the DT can be observed to be having these options. The first option is we're going to have a signal with the frequencies of 400 pi to pass through. Remember that the input to the filter got two frequencies value, 400 pi and 600 pi. So the first option that can be realized is that the output will be having only a single frequency of 400 pi. Second option is that also a single frequencies, but the frequency is 600 pi. Okay. The third option is that we are going to have both frequencies with 400 pi and 600 pi can pass through the filters. And the fourth option is that neither of them, I mean either 400 or 600 pi, both of them can pass through the filters. So these are the options that can be obtained, the possible values of the output of DT, depending on how we design the filters. Yeah. Okay. Right. So let us have a look on this explanation on the behavior between a relationship of the input CT and then the filter response of H omega and also the output of the T just now. Yeah. Okay. So if we refer back to the CT just now, yeah. So the CT is in terms of the exponential terms. So by using the table that we have learned last 2 weeks, yeah, last 2 weeks, this CT can be now returned in terms of its frequency domain value. Okay, you can refer back to your attachment, in which all the exponential terms can be returned in terms of a delta function, yeah, a delta function. So how can you obtain this from the exponential terms? So please refer back to the table, yeah. So the CT can be written as a C omega in this particular form. Yeah, we have a pi, a delta omega minus 400 pi. Okay, and the rest will follow suit. Yeah, so we're going to have four impulses. Yeah, four impulses based on this equation. So your C omega will be having these terms or these impulses, where we have impulses located at negative 600 pi, negative 400 pi, and also at the positive side it is at 400 pi and 600 pi, and the magnitude for the impulses are pi. Yeah, so how can we obtain this? So these impulses or these spectrum values are obtained from the equations here. Yeah, these equations. Okay, so these are the I can say this is the spectrum or the amplitude spectrum of your input, the C omega. Okay, and these are the scenarios that we can consider for the filters. So this is your H omega, which is the filter response. Okay, so the filter response can be designed such that we're going to have this kind of response, yeah, where omega c stand for the cutoff frequencies. Okay, so the cutoff frequencies in this first option, scenario number 1, is that omega c is said to be bigger than 400 pi value. but omega c is smaller than 600 pi. So that's why we're going to have your response of the filter to be look like this, in which if we multiply, if you multiply the h omega, this response of the filter, with the c omega, with the c omega, because if I can refer back to the previous diagram, in this diagram, okay, so c omega is the Fourier transform of CT, and as what we have learned before in lecture 10 and 11. So if the input in frequency domain pass through the filters, basically the response, I mean, the relationship between the input and the filter is basically a multiplication, C omega multiplied with the H omega. Okay, so that's why from this C omega, and for the first option, this is your response to the filter. The multiplication between the C omega and the H omega will result only these impulses at the output of D omega. Yeah. So previously we know that the C omega is having an amplitude of pi, the H omega is having an amplitude of G. So the new amplitude will be just a multiplication between them, which is G pi. Okay. And since the cutoff omega C is always smaller than 600 pi, so 600 pi will be filtered out. Yeah. So it can only permit the 400 pi impulses to pass through. So this should be the output of the filters when your response of the filter H omega is having this shape of response, in which the cutoff frequencies is smaller than 600 pi. Okay. All right. Hopefully it's clear. Yeah? Okay. So this should be the second scenario, in which we see that only 600 pi signal can pass through the filters. So this is the case. That should be the pattern of your frequency response. Yeah, in which that your cutoff frequencies will be located somewhere between 400 pi and 600 pi also, but the pass band, we call this as a pass band. So the pass band value is always bigger than 400 pi, or always bigger than omega c, as opposed to the previous case that we have here. The pass band is smaller than omega c. But for the second case, the second scenario here, because we want the 600 pi to pass through the filters, so our frequency response is made such that the cutoff frequencies, the passband frequencies, this is a passband value, the passband frequencies will always bigger than omega c. Omega c is located between 400 pi and 600 pi. So in between negative omega c and omega c, we know that from this diagram, your values of frequency response is 0. So anything between these cutoff frequencies value will be filtered out. Anything between its cutoff frequencies value will be filtered out. So such that when we multiply the input of C omega and the H omega, we are now going to have your output of D omega to be look like this. Okay, so it only permits the 600 pi impulses to pass through. Okay, so this is your output of the filters. For the second scenario case. Okay, so the third scenario is when we consider that both signals can pass through the filters. So in this particular case, your frequency response of H omega should look like this. But the difference is that your cutoff frequencies is now bigger than 600 pi. Okay, your omega c, the cutoff frequencies is said to be bigger than 600 pi. So when we have this condition of frequency response with the given specification of cutoff frequencies, so it means that all the impulses starting from negative 600 pi up to positive 600 pi, all of the impulses can pass through the filters. Because we have set the cutoff frequencies omega c here to be always bigger than 600 pi frequencies. Okay, so that should be the third scenario. While for the fourth scenario, we can also set the filter specification such that we are going to have this pattern of frequency response, but the omega c is chosen or is designed, omega c is designed such that the value is always bigger than 600 pi. So when we have this condition of filters cut off frequencies, which is bigger than 600 pi, and as what we have learned from the second scenario just now, everything or anything between these cutoff frequencies will be cut off or will be filtered out. Yeah, will filtered out. So that's why when we consider your output graph or output response, the omega, nothing exists. Yeah, nothing exists here means that there is no output due to this design of your filters frequency response. Okay, so this is how we use the Fourier transform to explain about the filter design. Yeah. Okay. Any questions so far on this first application of Fourier transform, the filters? Okay. No. Yeah. Right. So let us proceed with these examples here. We are having this example in which systems consist of two inputs still, where we have xt and cos 50t as the input. So the input are said to be mix, and this will produce the AT. So mix is basically it's a multiplication, yeah. So you're going to have the AT, okay, the AT. The AT signal is said to pass through the filters H1 omega, in which H1 omega is having this response, yeah, frequency response between 40 and 50 hertz, I mean 40 and 50 value of frequencies. Okay, and the output of the filters is BT. BT is said to be multiplied with the cosine of 100t, and the result of this multiplication will produce a CT. Okay, and CT will be then multiplied with the H2 omega, which is the filter response, the second filter response. And for the second filter response, it is between negative 100 to positive 100, the amplitude of 1. Okay, and the output is YT. So this is the system's the system's configuration. Yeah. Okay. Given now that the xt is 5 cosine of 10t, yeah, 5 cosine of 10t. So based on the given xt value, we need to obtain what should be your at, what should be your at, what should be your bt here, what should be your ct, and what should be your yt. So that should be the components of the systems that need to be calculated, yeah, that need to be obtained. Okay, so once you have these AT, BT, CT, and YT, you need to actually obtain a spectrum. Spectrum, this means that for the spectrum, what you have to do is that you have to find, you also need to find the A omega, B omega, C omega, and Y omega. Then only you can get the spectrum. So to find the spectrum for these first values, you need to first transform all of these AT, BT, CT, and YT into Fourier transform. Okay, so once you have the values in Fourier transform, then only you can get a spectrum for these four components, I mean for these four signals, yeah. And number three is we need to obtain the frequency response of H3 omega, which represent the components in the dotted box. So H3 omega basically is a combination of these filter response, means H3 omega is a combination of these system components, which include the H1 omega, H2 omega with the components of the signals inside here. So it means that H2 omega is simply a system between the AT, the input AT and the output of YT. Okay, so that should be the H3 omega. Okay, so let us proceed with this finding the AT, BT, CT, and YT first. Yeah? Okay. Okay. Right, hopefully you can view this board clearly, yeah? Okay, so we have a case, for the first case, is that we are having a relationship of AT, okay, is equals to xt multiplied with the cosine of 50t, yeah? This is the, based on this the systems diagram, yeah? The input AT, sorry, the AT is multiplication of xt and cos of 50t. And from these questions, is given that xt is 5 of cos of 10t. So we can write that the AT is equals to 5 of cosine of 10t multiplied with the cosine of 50t. Yeah. So we can obtain the results of this multiplication.
Doctor, we can't see the screen.
You can't see the screen.
It's black.
Let me try it one more time. Yeah.
Still same, Doctor. It's black.
Still black. Yeah. What happened? Can you view it now?
No, Doctor.
Oh, still cannot. Okay, what happened? What happened? What happened? Never mind. So it's not compatible, yeah? It's not compatible. Okay, can you view it now? This is a Jamboard.
Yes, Doctor, we can see it now.
Okay, thank you very much. All right, so let us proceed with this example just now. Okay, so we are given that from this systems configuration, can be written that your AT, sorry, okay, is equals to xt multiplied with the cosine of 50t. Okay, this is based on the systems configuration. Yeah, and we know that the xt is equals to 5 of cos of 10t. So based on that, we can then write that this is equals to 5 of cosine of 10t multiplied with the cosine of 50t. Yeah, right. So we can write this in terms of the exponential form. Yeah, because you want to find the Fourier transform for this equation. So again, we have this as equals to, okay, straight away we can have it as f 5 over 4, okay, exponential of j of 60t plus exponential of negative j of 60t plus exponential of j of 40t plus exponential of negative j of 40t. Okay, and we can have it in terms of the Fourier transform as equals to a omega. So we're going to have the Fourier transform. So this should be equals to 5 over 2 pi. Okay, and we're going to have sigma omega minus 60 plus sigma omega plus 60. Okay, plus, okay, sorry, don't have enough space for this. Sorry for this, yeah. So I need to refer to the next page then. Sorry for that. Okay. Sorry for this interruption. So we're going to have a omega. Yeah, your a omega will be equals to 5 over 2 pi. Okay, impulse function omega minus 60 plus impulse function omega plus 60. Okay, plus impulse function omega minus 40 plus impulse function omega plus 40. Okay, so that should be the impulses, the A omega, which is obtained from this AT, yeah? From this AT, okay? So a transformation from exponential in time domain will result in a impulses, okay? You can refer back to your notes, yeah? To the table, in which you're going to have these as the A omega, right? And basically from here, you can have a relationship between the input and also the system response just now. If I can go back to your slide. Okay, this is the case, yeah? All right. Your A omega just now, they actually have four impulses. Yeah, if I can sketch it in here. Okay, I'm going to have, okay, for the A omega, we are supposed to get, okay, this is your A omega, yeah, I'll sketch it for you. So we're going to have four impulses, okay. So located at negative 40, plus 40, 60, and negative 60. This is obtained from the previous equation with the amplitude of 5 over 2 pi, okay. That should be the amplitude of your impulses. And note that there is a multiplication now because the A omega need to be multiplied with the filter response of H1 omega and is given here, okay, which is between 40 and 50. So basically, if we base on that, we're going to have this is your, sorry, that should be the case, yeah, that should be your filter's response, okay, between 40 and 50. And if we base on this, multiplication between the A omega and H omega will result on the impulses at this position, which is at negative 60 and positive 60. Sorry, negative 40 and positive 40. Whereas the 60 impulse and negative 60 impulse, both of them will be filtered out. Yeah, will be filtered out. So as such, I can rewrite that for the output, which is the B omega, okay, if I can sketch it here, so the B omega, which is the output of your filters, you'll be having two impulses located at positive 40 and also at negative 40 with the amplitude of 5 over 2 pi. Okay, so that should be your B omega, yeah? Okay, you got the point there? Okay, so if you have any question, please ask, yeah? So from here, we can then obtain your BT because from the question, it requires us to find the BT, right? Find the BT. So we obtain here is a B omega. We have obtained the spectrum, yeah, which is basically answering the second questions here. Okay, so the B omega, we need to do the inverse Fourier transform to find the BT. And we know that from this relationship of, from this diagram, your B omega is written to be 5 over 2 pi with a delta omega minus 40 plus delta omega plus 40. Okay, that should be your equation for the B omega. So we're going to have inverse Fourier transform that should give us the BT. So BT can be returned straight away to be equals to 5 over 4 exponential of j of 40t plus 5 over 4 exponential of negative j 40t. Okay, that should be your BT. Okay, in which we do the inverse Fourier transform for this B omega. So we're going to receive and we're going to get the BT as this. Yeah. Right, any questions on this B omega spectrum and the BT equation, mathematical equation for the BT? Hopefully okay, yeah? Right. Sorry for that. All right. So next is to find the CT. Okay, to find the CT. So let us proceed to find the CT. Okay. So from the diagram, okay, from the system, we can write that your CT will be equals to BT multiplied with the cosine of 100t. Okay, and we can, and it's given that the C omega or the CT itself can be written to be 5/4 because we have obtained the BT just now, exponential of J 40t plus exponential negative J 40t, and the cos of 10t is written to be exponential of J 100t plus exponential negative J 100t divided by 2. Okay, and further on, we're going to have the result for this will be 5/8. Okay, exponential J 140t plus negative 140t. Okay, plus exponential J of 60t, exponential negative J of 60t. Okay, right. So from this equation, we can then do the Fourier transform for the CT. Okay, going to have the C omega. So that will result at a value of 5/4 pi. Okay, so we have 4 impulses located at 140. Okay, also have impulses at plus 40, which is at negative 140. And then we have impulse at positive 60 and also impulse at negative 60. Okay, so that should be your C omega. Yeah, C omega. All right, and the C omega, we can sketch it to be look like this. Okay, based on these values of C omega, the equation, we are going to have the C omega to be look like this in terms of its spectrum. Okay, that should be your C omega. Okay, we're going to have 4 impulses located at 60. Then we have at 140. Here is located at negative 140, not negative 60 and negative 140. Okay, so there should be 4 impulses. Okay, 1, 2, 3, and 4. And the amplitude for these impulses are 5/4 pi. Okay, so that should be the impulses position, yeah, which are based on the equations that we have derived before, and with the amplitude of 5/4 pi. Yeah. Okay. And if we can recall back, the CT or C omega will be then multiplied with the H2 omega, which is the frequency response of your second filters. So if I can sketch back the second filters, which is H2 omega, okay, this is H2 omega. You can refer to your notes, yeah. So this response will look like this, located at negative 100 and positive 100 with the amplitude of 1. So these two responses shall be multiplied. Yeah, so when we multiply, we're going to have that, we can say that 140 impulses will be located outside. Yeah, located outside this H2 omega. So 140 impulses will be filtered out. So we are going to have only a impulse at 60 and negative 60. So the results of multiplication will be then produce this output, which is Y omega. Okay, and Y omega will be located at positive 60 and negative 60 with the amplitude of 5/4 pi, and the same thing is applied for this, which is 5/4 pi, the same things. How can we obtain this? Because multiplication between C omega and H2 omega. So why we need to multiply? So remember, if you go back to the question just now, the input to the system H2 omega is C omega. So we need to multiply both response so that we're going to have the output of Y omega here. Okay. So bear in mind that why we have 60 as the impulses at the output, because 140, if you multiply with this response, 140 is located outside, yeah, located outside this response, so it cannot be considered, yeah, so it'll be filtered out. So that's why we have the y omega should be look like this. Okay, so in terms of the equation for the yt, which is the Fourier transform, sorry, inverse Fourier transform for the y omega. Okay, so from this equation, I mean from this y omega, we can write that the y omega, okay, y omega is equals to 5 over 4 pi impulse omega minus 60 plus impulse omega plus 60. Okay, so that should be your y omega. So to find the yt, need to do the inverse Fourier transform. We're going to have the yt, okay, and we're going to have the values as 5 over 8, okay, exponential of j 60t plus exponential negative j 60t. Okay, so again, I will advise you to refer back to this table, yeah, in which if we refer to the table, basically, I need to write this for you. So exponential of j omega naught t, for transform for this will give us pi, okay, or 2 pi delta omega minus omega naught. Okay, this is based on the table. Yeah, that's why when we have equation of 5 over 4 pi delta omega minus 60, for instance, your time domain for it will be 5 over 8. Yeah, 5 over 8 exponential j of 60t. Okay, then hopefully it's clear, yeah, on this yt. I mean, for this particular case is the yt and also the spectrum of y omega. Okay, any question on these issues then? Any questions so far on this example number 1? No. Okay, so if there's no question, let us proceed with this the third questions here, which is to find the frequency response of H3 omega. Okay, this is one. Yeah, this is the one. Okay, so to find the response for H3 omega, so it's good if we can see that for this particular H3 omega, the input to the system is AT or A omega, and the output is YT. Okay, so to find the H3 omega, so what can we do is that we need to first sketch what should be the A omega, yeah? What should be the A omega, which is the input to the filter. So A omega, if you can recall back based on the previous part 1 here, yeah, or part 2 here, which is the A omega, it can be sketched that the A omega should be look like this, yeah? Your A omega, yeah, your A omega will be having 4 impulses, okay, located at 40, 60, then we have at negative 40, and we have at negative 60. Okay, so that should be the impulses with the amplitude of 5 over 2 pi. Okay, so that should be the amplitude for the A omega, yeah? Right, and then for the output of y omega, which is based on what we have done recently, so the y omega is only got 2 impulses, which located at 60 and located at negative 60, and this is having the amplitude of 5 over 4 pi. Okay, so in between this A omega and Y omega, sorry, I forgot to label, this is Y omega. So there is a systems, okay, there should be a systems, which is your H3 omega. Okay, that's should be the H3 omega. So basically, you are requested to find what should be the frequency response for H3 omega such that when the input is this, 4 impulses located at this location and with this amplitude, so the output is only having 2 impulses located at these positions and the amplitude of 5 over 4 pi. So what should be the possible response for the H3 omega? So basically from here, we can say that the response for the H3 omega will be look like this. Yeah, if I can sketch it here. Sorry, okay. So for the H3 omega, Okay, based on that condition of the input and the output, you're going to have that should be the response, in which the amplitude for this response will be equals to half. Why half? Because if the input is 5/2 pi, output is 5/4 pi, so it should be half, yeah. Whereas that should be the omega c position, and that should be the negative omega c, in which your omega c, yeah, clearly must be, I can say the value of omega c must be bigger than 40, but less than 60. So that should be modulus, yeah, modulus of omega c, because we have positive and negative side, yeah. So omega c, the cutoff frequency's value shall be smaller than 40, so be bigger than 40, but less than 60, such that when we consider the position of omega c between these two frequencies value, so everything bigger than omega c will be passed through, which include the 60 impulse, but the 40 impulses will be filtered out. So that should be the answer for number 3, which is the frequency response for the history omega. Okay, any questions so far on this example number 1? No, yeah? Okay, if there's no questions, let us proceed with the next example here. Okay, so we are given again about the same problem where we have the input of xt. Okay, so we have the cos of 10t as the input also. Then about the same, yeah, it's about the same system configuration, but the difference will be on the inputs. Yeah, on the inputs where you have the x omega. It's now given in the form of this signal, yeah, from -1 to +1 with the amplitude of 1. We also given the h1 omega, the frequency response between 9 and 10. Okay, and then we have the h2 omega between -1 and +1, with both of these amplitude are equals to 1. Yeah. Okay, so these are the case. The question is number 1, sketch the response of A omega, B omega, Y omega, and C omega, in which we need to find what should be the frequency response for all of these time domain AT, BT, CT, and YT signal. Okay, yeah? Okay, hopefully it's clear, yeah? Right, so let us proceed with the solution for this example. Yeah, okay, sorry. Okay. Right, so if we can write the equation for the system, for the AT, yeah? So AT can be written to be equals to xt multiplied with the cosine of 10t, sorry, 10t, yeah? So by using the modulation properties, yeah, we can write that the A omega in the Fourier transform, okay, shall be equals to half of x omega minus 10 plus half x omega plus 10, yeah? Okay, that should be the equation. Sorry, so it's supposed to be like this, sorry, yeah? Rub this. Okay, then that should be 10 here supposedly, right? So from your x omega is given to be in this particular form. Sorry, yeah, not that nice when drawing. +1 and -1 with the amplitude of 1, yeah? And that should be your x omega. So based on the given x omega here, and this is the equation for the A omega, so we're going to have that the A omega can be written to be based on the x omega here, in which the x omega shall be shifted by 10 units to the right, and then also shifted by 10 units to the left. And the amplitude for both of these x omega, which has been shifted, shall be reduced by half. Yeah. So for these, we're going to have that the x omega, yeah, which has been shifted to be look like this. This is at +10, and this is at -10, and the amplitude is at half. So this is of this is 9, this is 11, this is -9, and this is -11. So that should be your A omega. Yeah. Okay. And if we can recall back to your diagram, yeah, your system equation is given by, I mean, for the H1 omega, okay, H1 omega is given by this, okay. Sorry, I apologize, sorry for this, my mistake. Okay. Okay. So if you can refer back to the questions, okay, your H omega will be look like this, okay, which is at 9 and 10, and also here which is from -9 and -10 of 1. Okay, and if we're referring back to the A omega just now, we can refer back to the previous A omega. Okay, yes, omega. So A omega will be the input to the H1 omega just now. So we can say that when we multiply this A omega and this H1 omega, I forgot to put this is H1 omega. Okay, so multiplication between the two signals will result at the output of B omega, which is the output of the system, will be only a portion of a signals of A omega, which will be from 9 to 10 only. Yeah, which is from 9 to 10, and also from -9 to -10 with the amplitude of half. Remember, B omega is the output which is due to the multiplication of H1 omega, which is the system, the filter frequency response, and the A omega. So A omega is having this signal from 9 to 11 and from -9 to -11. Okay, multiply with this H1 omega, which is only from 9 to 10. So as a result of this multiplication, you're going to have your B omega should be looked like this only. Okay. Okay, hopefully it's clear, yeah? Right, and then if you can again refer back to the questions, we can have a relationship between the CT and BT, in which the CT equals to BT multiplied with the cosine of tan t, okay, and by using the Fourier transform, which is a modulation, we're going to have a C omega, yeah, C omega, this should be equals to half of B, sorry, B, this is B, omega minus 10 plus, half B omega plus 10. Okay, that should be the case, yeah? So we are supposed to get the C omega should be based on this B omega, which shall be shifted by 10 units to the right by 10, yeah, and 10 units to the left. So that will give us the C omega. So how does C omega should look like? So based on the B omega, which will be shifted by 10 units to the left and to the right, we are supposed to get C omega will compose of 4 different signal, yeah, 4 different signal, in which if we can sketch it, yeah, your C omega, okay, so I think I need to make it longer for this part. Okay. All right. So the C omega should be having this pattern, which is from 0 to 1, and that should be 0 -1, and the amplitude is now 1/4, and that will also be having these signals positive 19 to positive 20, and also then we have -19 to -20. So how can we obtain this signals of C omega? So we go back to this diagram, yeah. Okay, so from here we notice that C omega is due to B omega, which will be shifted by 10 units to the right and 10 units to the left. Okay, so we consider for the first diagram here, yeah, for the first signal here, which is from 9 to 10. So when we try to operate, yeah, when we try to implement this equation to this particular signal, okay, you're going to have now that the amplitude shall be reduced by half, supposedly, because half here, and we have multiplied with half, so we're going to 1 over 4. So this signal will be shifted by 10 units to the left, which is located at this position. Yeah, this position, which is between -1 and 0, right? Then it will be shifted by 10 units to the right, which will be located at positive 19 and positive 20. And the same things applied for the second signal here. It will be shifted by 10 units to the right, which will be shifted to here, which is from 0 to 1, and then to the left, which is from -20 and -90. That is why we are getting the C omega, which will be look like this. Okay then, hopefully it's clear, yeah, on how you obtain the C omega, in which I repeat again, the C omega is obtained based on the shifting of the B omega signal according to this equation. Okay, the C omega is obtained based on the shifting of B omega by 10 units to the right and 10 units to the left. And the amplitude for the B omega shall be reduced by half, then that will be the amplitude for the C omega, yeah? Okay then? Right. And if you can recall back regarding this H omega signal, okay, so H omega signal is look like this. H2 omega is located between -1 to +1. This is H2 omega, yeah, H2 omega. From -1 to +1 is the amplitude of 1. Okay, so when multiply this C omega and H2 omega, so we are going to retain only this portion. Whereas for this portion between 19 to 20 and -19 to -20, these two portions will be cancelled out or be filtered out. Yeah. So as a result, you're going to have your Y omega, okay, will be look like this, nah? Yeah, which is -1 to +1, and the amplitude will be equals to 1 over 4, because 1 over 4 multiplied with 1, yeah, this is 1, yeah, that is 1, so we're going to have this, nah? So that should be your Y omega. Okay, so that answers the questions that we have in this example. Any question related to this example? Okay, hopefully it's clear. Yeah, thank you very much for your response. Okay, right. So for this example, I'm not going to do this. I hope you can try to do this on your own, because basically it's the same as what we did in the previous example. Okay, maybe the difficult part is on the X omega, how to get this X omega. That's all, yeah. So once you have the X omega, you can proceed with finding the E omega, finding the H omega, F omega, and so on, yeah. So try to do this on your own. If you got problem with these solutions, you can always PM me, yeah, for further discussion. Right, so that's for the filter. So after this, we're going to proceed with the amplitude modulation, the second application for the Fourier transform. So we are going to have a break for 5 minutes. We're going to get back here at 12:05. Okay, so please have a break for 5 minutes. Yeah, so we're going to come back with the next topics of amplitude modulation. Okay, thank you.